Now that we've laid the groundwork to simplify radical expressions in our last section, we're going to be working with what we call binomial radical expressions, starting with 6-3. Binomial just meaning that we have two terms in our expression. Last time we left off, we were multiplying and dividing our radical expressions when we were combining them. Here we're going to look at sums and differences, so that's going to be adding, subtracting. And like we do with any other kind of adding, subtracting, we do need to make sure that we're adding and subtracting like terms. In this case, we're going to call them like radicals. And for that to be true, we need two things to match in that case. We need the index to be the same, and we also need what's inside the radical expression, so that would be what we call the radicand. We need that to be the same as well, or else we're not going to be able to combine these. So if I'm to add or subtract in our first example, again, I just want to check and see that the index matches. Square root, it looks like our index is the same. 7bc and 7bc, so it looks like our radicands are the same, meaning that we do have like terms. And now, like with any other kind of expression, I can just add, treating these almost like with just coefficients, the pieces outside of your radical expression, keeping everything on the inside the same. Almost like if I just took 14 times x and 2 times x, combining those outside parts together, I just get 16. Looks like this is a on the outside, and I still have a square root of 7bc on the inside. That's going to be the addition of just those two separate terms. If I was to try that with the second example, again, feel free to try to work ahead on these next two as well. It looks like these are actually not like terms because we have a different index for those. I have a square root for the first and a cube root for my second term. And if I was to try it again on part C, it looks like we run into a similar issue, except this time that the index matches, we still see that the radicands, x and 3x, if those parts aren't the same, these are also not going to be like terms, so we're not going to be able to add those two. Not exactly a new rule in our next example, but more of an extension of our last rule. We can add or subtract these radical expressions together as long as they have that same index and radicand. And although these don't look like they match at the beginning, they do all have the same index of a square root, but I have obviously three different radicands on the inside. What we do want to make sure of is that if I was to simplify those first, we may actually have a match that it doesn't appear that we have at the beginning. So simplify, just as in our last section, we want to think about if these are square roots, any perfect squares that would be factors, like 2 would be a perfect square factor of my first term. If I'm to think of, again, 175 would be 25 times 7, it looks like, 25 being another perfect square. 63 is 9 times 7, 9 being another perfect square, meaning if I took a step to rewrite these, I could rewrite the first term as 2 radical 7. Again, since the 7 is still inside of my radical expression, we're able to factor out a 5 from the next one, but that's still radical 7 left over. We also have, it looks like 3 is a perfect square, but 7 was not. So now, just like in our first situation, if I'm to combine these, now that I actually do have like radicals, now that 7 is on the inside of all those expressions, I can just add up those just with the coefficients, so like 2 minus 5 and a plus 3, all on the outside. Radical 7 was our like terms for all three of those radical expressions. In this case, we actually do get kind of a rare case of the cancels. 2 minus 5 is negative 3, plus 3 more makes that a 0, so rather than just writing 0 radical 7, we just know that the final answer there is going to be 0 overall. We can even do this with cube roots. If I was to take a cube root of 250, for example, we just want to think of now perfect cubes that may be factors. So 125 is 5 cubed. That's a factor of 250. We can also factor out 54 the same way. 27 times 2, 27 is another perfect cube. 16, a little bit awkward to factor it this way, but 8 times 2 means that 8 is a perfect cube. These are all parts we'll be able to simplify outside of our radical expression, and the leftover 2, it looks like that's matching. That's going to create those like radicals. So again, if I rewrite this, 5 is a perfect cube. I was left with 2 in that first expression, or first term rather. 3 was our perfect cube. In the next term, I was still left with that 2 as a cube root. And then in the last one, we do want to make sure that this is also minus for the last one. Minus, it looks like 2 is our perfect cube. The cube root of 2 that I was left with on the inside is going to be my expression. So just like on our last situation, I just want to take those expressions together. 5, 3, and 2 on the outside, since now we have like radicals, and those are all a cube root of 2 that's left over. It looks like this is a case where I get 8 minus 2, so this is more traditionally what you'd see. Just a number that's left over in front as a coefficient. These are all the same like radical cube root of 2, and that leaves us with our simplified answer. Trying it with the next two, again, notice that we would have to simplify these next two questions as well to see if we can combine them in the first place. From the looks of it, we don't have like radicals, but if I was to simplify first, it looks like these are all perfect squares, or they do contain at least perfect square factors for my first two terms. 12 can be written as 2 squared times 3, and 75 can be written as 5 squared times 3 as well. So since these all end up having a like radical, that square root of 3, we can do the same thing we did on that last question, combine the coefficients on the outside, leave that like radical the same. Again, notice just like how I don't add x's, I don't add these like radicals, we don't get like square root of 9 or anything. I just get that same square root of 3 left over for my answer. And again, even with cubes, it's still going to work as long as I'm taking that cube root and I can factor out any kind of perfect cubes from my expression. Looks like cube root of 2 is as simple as we can get, but if I take the cube root of 16, as we saw with that last example, 2 cubed is a factor, so if I remove that from my radical expression, I can then just add those two coefficients, 5 and 2, so that's going to make 7 with the cube root of 2. And from the looks of example 3, it looks like we're not quite done with multiplying these radicals yet either, although now that we're talking about these binomial radical expressions, again, binomial referring to just 2 terms in each of those different expressions, we can multiply this instead of just a single term all written basically next to each other. And if you guys notice the structure of what I set up for my solution, this can be taught a bunch of different ways. I teach this in Algebra 1 using what I call a box method. Again, you might have also heard like foiling, first term times first term, outside terms, inside, and then last is another way to do this. But as long as I'm multiplying with 2 binomials, the way I'm going to set up my box method is I'm just going to list the outside portions of this 2 by 2 square with looks like the terms that we have from each of those expressions. So first expression written across the top, second expression written across the side. And this is just a handy way to use as a visual to do that same kind of step as you would from the FOIL method. I'm looking to multiply basically just the outside portions of my box together and almost find these as exactly like we would find like an area question, like a length times width. So if I want to multiply in the first box, 3 times 2, that should give me a 6. We just want to be careful when I multiply a radical expression times something just like 2. 2 times 2 would multiply, but I'm just left with the square root of 5 on the radical expression. And then similar, if I do 3 times 4 rad 5, the 3 and the 4 can multiply, but the radical that's left over is that radical 5. And then for my last box, I think to make this step easier, again, it's almost like terms. You multiply the coefficients together, so you're going to get an 8. And if I was to multiply radical 5 times radical 5, easy way to think of that is that it basically just cancels your radical. Or you can also think square root of 25 is going to give you that same kind of simplified answer. But either way, we have 2 things to multiply here, so I would take one more step and just know that as a final result, we would just get 40 if I was to multiply those last 2 terms together. Again, you'd be multiplying the same kind of terms if I was to use the FOIL method. Just like a visual if you want to set this up as a box, almost like a Punnett square if you guys have seen that in a science class. We're still looking to simplify what's left, so right now I have 4 separate terms in those 4 separate squares, but we're going to see that we have like terms along the diagonals, 6 and 40, noting that we just multiplied 8 and 5 when we simplified that bottom right square. 6 and 40 combine to make 46. If I'm to add up these like radicals, again, it looks like we have a square root of 5 and a square root of 5, so if I just add those coefficients, I get 16 with a root of 5. But that's now my multiplication, again, taking very similar steps as you do in Algebra 1, to just multiply 4 times and to be able to combine what's left. That's going to create my simplified binomial expression. If I want to try to take the same steps on those other ones, again, I just kind of did one real quick as an example, but see if you guys can do those others before we get to them. Just revealing those answers now. Let's see what those look like. Again, if I start with that same kind of beginning point, I just write my first expression off across the top of my box, writing the expression second expression down. Again, doesn't really even matter which part you put on which. I could have flipped these 2 sides, going to give us the same answer. As long as you know that you're then multiplying each square, 4 times 5 to get 20. 2 rad 2 times 5 gives us 10 rad 2. 4 times 4 rad 2, if I was to multiply in this square, I get a 16 rad 2. And then to finish, kind of like we've seen from before, 2 times 4 gives you 8, but then also if I multiply the radicals, they would just leave me with 2 without the radical sign. That's going to combine to make 16, kind of like how we got that 40 in the bottom right corner of the previous question. But I'm still not done. We have to make sure that we're combining any like terms that are left. 20 and 16 make 36. That's just going to be a constant, it looks like. And then if I was to combine the radical terms, now that those are like radicals, rad 2 and rad 2, I can add the coefficients, so that's going to make a 26 rad 2. Trying that one more time, it's actually kind of leading us into our next example when we talk about conjugates, not quite conjugates, is that we can take that same 2 expressions, write them across the top, write them across the side, multiplying each square, and here if we're taking that same simplification step, I guess here it's just a little bit more simple on that last box, rad 7 times negative rad 7. We just know that the radicals again will cancel and just leave us with a 7 by itself, no coefficient here to multiply and combine. It looks like we still have like terms we can combine. 15 minus 7, I got 8. Negative 5 rad 7 and positive 3 rad 7. We do want to be careful about the sign there, but that's a negative. We do get minus 2 rad 7 as the second part of our answer. If we're to multiply what we call conjugates, our work actually isn't any different from our last example. Notice that I still have my box set up, But what I mean by a conjugate is notice that I have 5 plus 3 rad 2 and then 5 minus 3 rad 2 as well, set up in this sort of way with just two terms being the same, and the only difference is that one you have a sum and one you have a difference. We're going to be able to use this kind of a concept to lead us towards our last example if I ever want to what we call rationalize another denominator. But again, first on this question, just make sure we can take the same approach as before. 5, 3 rad 2, write that across the top. 5, negative 3 rad 2, writing that down the side. And now if I'm to multiply in each box, I get 25, I get a 15 rad 2. Now I have a negative 15 rad 2, and it looks like, oh, what was that? We have a negative 15 rad 2, and it looks like we have a negative 9 times 2. If I'm to multiply the individual pieces, combining to make negative 18 on that last box. Again, I'm taking 3 times negative 3 to get negative 9. And the radicals, you can think of them as canceling or the square root of 4. Either way, that's going to simplify to get 2 for the second part of that answer. And as we've seen from before, 25 minus 18, that's just going to make 7. The tricky part about conjugates, though, is that notice that we actually have a match. We have a 15 rad 2 and a negative 15 rad 2. So that conjugate idea, we see this also in Algebra 1 when I combine with those same type of terms, is that those actually end up canceling. I just get a single answer like 7. If I was to try the next example, we see something else going on, again, pretty similar. 6 rad 8, negative 6 rad 8. If you were to do the work there, it would cancel. And notice we're doing the same thing in the other squares, 3 times 3 to get 9. Again, I just multiply this last part in two separate pieces, multiply the coefficients and multiply the radical expression. That's going to give you a negative 32. If I combine the like terms, we do get a negative answer. And again, notice that since they cancel out here, that's because, again, we started with what we call a conjugate. Looking at one more example of a conjugate, just start off the same way. 4 rad 5, 4 minus rad 5, just label the outside parts of our box. Multiplying each of our squares, and again, we'll notice that along the diagonals, if I am using a conjugate, we should have the radical portions canceling. Positive 4 rad 5 and a negative 4 rad 5 means that all that we're left with for an answer is going to be that 16 minus 5 to combine to get positive 11. And if you're wondering why it was important to multiply kind of a conjugate or multiply conjugates together, it's because we use that kind of a step to rationalize this sort of denominator. Notice that we did this in our last section, but we just had a single term, so something like radical 3 on the bottom. If you remember our step from earlier, we'd have to do something like multiply by radical 3 over radical 3. But now that we have two terms, so again, we call that a binomial term for a denominator, we're still going to have to rationalize it, but notice how my last few answers ended up. We're going to be able to remove a square root portion of my answer by using the conjugate instead of just using a single term. So when I multiply, just like with any other fraction, I do want to make sure both the numerator and the denominator are multiplied by the same expression. Otherwise, just like any other fraction question, I'm going to change the value when I don't want to. And for the numerator, it's easy enough. I could just distribute, remembering that the radical portions multiply, but I'm just left with the 2 as a coefficient. So rad 7 times rad 3 gives me rad 21 for the first term. And then since I have another 2 in front, rad 7 times rad 5 is going to get me, it looks like 35 for my second term. Since we do have to multiply these two conjugates across the bottom for my denominator, I'm just going to do this work using that same kind of box method as before. Again, it doesn't really matter which term you start with. I just start with that first one across the top, and then the bottom one, or sorry, second term down your side. Multiplying each square means that, again, if I was to multiply a radical times a radical, this could be a square root of 9. Or you could just think that that's going to simplify the radical and just give you 3. We get, looks like, a negative radical 15 from our first multiplication, a positive radical 15 from our second. Notice that same idea with conjugates applies here. And then if I was to multiply in that last bottom square, again, radical 5 times a radical 5 essentially cancels that radical sign, and now we're just left with the negative 5 as a final answer in that bottom square. I still do want to take the same steps as before, so it looks like 3 minus 5 gives us negative 2. The whole idea here is that our radical expressions should cancel since we chose to use those conjugates. And now since we still have the numerator to deal with, let's just rewrite this, what we have so far. We had the numerator from before, so we're just saving the top part of our answer. And the bottom part, again, we essentially just did all of this work to figure out that we could simplify the denominator as just negative 2. But I still want to watch out for any more simplification steps. It looks like negative 2 is a factor of both of those terms for my numerator. So that's going to divide and just give me negative 21. Going to divide and also give me, it should be another negative. Looks like negative radical 35. And that looks like is going to be my simplified form. Again, noticing that we rationalize the denominator, there are no more radical expressions left on the bottom of my fraction. Taking the same steps on the next one, again, first you just got to think of your conjugate. Conjugate's not going to change any of the expressions, or sorry, the terms rather. It's just going to change that from minus, it looks like, to positive. We could distribute it across the top, so rad 5 and rad 2. If I was to multiply that times my original expression, noticing that the radical 2's actually cancel out and just give us something like 6. If I'm to look at the bottom of this and multiply again with those conjugates, we just get that, I believe, to be a 3. So taking the numerator, dividing that by our new conjugate, which was just 3, that's going to give us our simplest form of that last expression.